Welcome everybody to today's RISA webinar, all about the new seismic provisions that we've just added into the program. And I'd just like to make a quick mention that although the title of this was regarding the AISC 341 provisions, we're also going to be covering the 358 provisions today, for those of you who are familiar with that. So at this point, I'd like to point out that the versions of the software I'm going to be using today are both brand new. This is RISA-3D 9.1 and RISA Floor 5.1. These versions were just completed here at RISA, and we're currently in the process of uploading these new versions to our website. So those of you who are currently under maintenance with us will automatically receive these in the mail over the next few weeks. And anybody else who wants, I would say starting about tomorrow, you should be able to get these directly from our website. Now, all the new seismic provisions have been added directly into RISA-3D, but it will also still work when you're using RISA-3D underneath RISA Floor. And in today's example, because we're going to be working with a building model, it'll be most appropriate to do RISA-3D under Floor. But of course, those of you who only have RISA-3D and perhaps you do industrial type structures more often, everything you see here today you can do exactly the same in RISA-3D on its own. Now, the codes we're going to be talking about today are the AISC codes. All of the seismic provisions that we've put into the program are currently for hot-rolled steel. Now, if we take a look here, there's actually three codes we're going to be referring to. And this first one is one that we've gotten a few questions on over the last year since version 9 came out, when we changed the name of the code in the program from 13th edition to AISC 360. The reason we did that was in order to avoid confusion between the 360, the 341, and the 358, although that has actually caused some confusion. So now in the newest version, we actually refer to this as the 360 parentheses 13th edition, just to clarify. Now, the 360 is the traditional steel manual that we've all used, and it's used for non-seismic steel designs. Now, a partner document the AISC has come out with is the 34105. This is the Seismic Provisions book here. And this is going to cover all sorts of additional steps that you need to take for high seismic buildings. And then we also have the AISC 358, which is packaged inside of this seismic design manual, and this goes over pre-qualified seismic moment connections and all the details and variables and the such that are associated with those. Now, when it comes to seismic design in the structure, there's three main considerations we need to take a look at, and that is the strength of the members to hold up against the seismic forces, the strength of the connections to hold up against the seismic forces, and of course the seismic drift. Now, a majority of what we've done in the program for this latest version has been revolving around member strength, and to some degree connection strength as well. As you'll see, we'll actually design your members and give you full code checks based off all the seismic provisions. With regard to the connections, we currently don't have seismic connection design in the program, although that is on its way. And we're going to have connection strengths reported in the current version of RISA-3D. Now, as for drift, we haven't made any changes in this release to the way that we report drift, but we will eventually be making some improvements to that as well in a future release. Now, to begin with, we have the response modification coefficient, the R factor that you should all be familiar with. And I'd just like to point out that in previous versions of RISA, before we had any seismic detailing, the program was set up to design any structure for which R equals 3. And when you set R equal to 3 and you take a look in the AISC 7, what you're referring to is a steel system not specifically detailed for seismic resistance. And so this is traditionally how things have been designed through RISA, but of course now we have the capability to take it even farther. Now, if you take a look in the code, it does mention that R equals 3 is actually only valid for seismic design categories A, B, and C. And in general, if you can use R equals 3 and your seismic forces aren't too high with regards to A, B, or C, then you can actually get quite a bit of savings and do a lot less engineering by setting it this way. But of course, we recognize that a number of parts of the country are a little more seismically active, and setting this R equal to 3 may not even be allowed, and even if it is allowed, in some cases it can be way over-conservative in terms of the forces that are created, since R is in the denominator of the seismic base shear equation. Now, there's a couple other variables that we're going to be referring to today, and there's a lot of confusion amongst people regarding these variables, so I wanted to talk about those. One of these is omega, the overstrength factor. Now, the overstrength factor is applied to load combinations, and so this is a factor that increases the effects of your seismic forces. But the increased effects for the seismic forces don't need to apply to all the members in your structure. Only certain members that are part of the lateral frame system that's going to be taking the seismic load. Now, the meaning behind the overstrength factor is that certain members during an earthquake scenario must remain elastic no matter how high the earthquake forces get. And so what this does is this increases the force that we design for, and of course we're designing in the elastic range when we're using the standard AISC design methodologies, and so this basically gives us a design for the member for which it will remain elastic for much higher forces than the standard seismic design forces. Now, as for when you use the overstrength factor, that's dictated within the Seismic Provisions Manual. Another important factor to consider is rho. This is the redundancy factor. This also applies to load combinations, and this actually applies to all members in your structure which are not using the omega overstrength factors. So it actually ends up becoming conservative. You're sort of double dipping if you amplify your seismic forces with a redundancy factor and with an overstrength factor as well. And so the redundancy factor is something we're going to apply to all other members. And its usage is dictated in the AISC 7 as opposed to the seismic provisions. Now, with regards to the frame types that we have within here for the design, if you take a look in the seismic provisions, they refer to three basic types of frames: moment frames, brace frames, and steel plate shear walls. Now, for this release that we've just come out with here, version 9.1, we're going to be covering moment frames with all the different associated moment connections that go with them, and we're going to be covering concentric braced frames. Now, in future releases, we plan on looking at adding the eccentric brace frames and the buckling restrained brace frames, and possibly even the steel plate shear wall. But since these frame systems here comprise a majority of seismic framing systems, we figured we would start with the common ones first. So without any further ado, let me go ahead and load up a model here that I've created. And this is called the podium building that I've built because it's a building that's designed as a concrete building on the first floor and steel structure on the floors above. So that way we can take a look at how mixed materials are going to interact in terms of a vertical seismic load resisting system. So you'll see that I've opened up RISA floor here, and let's just get a look at this model. If I scroll around a little bit, you'll see that it's a 3-story model and that we have some concrete beams and shear walls at the first floor and steel on the other floors. Coming into the plan views, we can see on the roof we have steel joists, and we have some steel moment frames set up, and the moment frames are designated as lateral members. If I take a look on the third floor, here we have a composite steel flooring system, very similar. And then coming down to the second floor, this is all the concrete that we have here. Now, I've already solved this model, and I've already set it up because I felt we could gloss over the basics of RISA model building. Today's session is going to be all about the seismic detailing specifically, so I'm going to assume that you're already capable of getting the model to this point, which is basically a model that's been solved and designed but not yet detailed for any sort of special seismic provisions. So I've actually already solved this model and saved the results. And so now I can use the Director tool, and we're going to go straight into RISA-3D. Now, when we're in RISA-3D, the first question that we're going to get here is on the seismic loads. You always get this popping up when you transfer between floor and 3D. And so let's review briefly the seismic loads that I've already applied to this structure. So you can see here, this is using the AISC 705 code. We're using occupancy category 1 or 2. That's just going to be a 1.0 importance factor, basically. Now, the long period and the spectral accelerations were all taken from a location here in Orange County, California, so that way we can actually get some rather high seismic forces applied to this structure and make it worth our while to apply the seismic provisions to it. We're just using the standard estimations of building pyramid, period, and then the R factors that we're using here are going to be 3. Now, this is just the initial R factors that were used to size everything in this building. And what we find is that when the program automatically calculates our seismic loads, it figures out that we fall in design category D. And when we're in design category D, that means that the usage of R equals 3 is actually not allowed. But let's take a look at how the building does perform anyhow under R equals 3, even though we have this higher seismic design category. I'm going to hit OK here. And the next thing we get is the global parameters. And this model, incidentally, will be available up on our website after the fact so that you guys can play around with it once you download the new version. Now, when I come up here in the global parameters, I'm going to go to the codes tab first off, and we'll see that we have the AISC 13th, which is the 36005. And I'm going to solve this model using LRFD because I'm also using concrete shear walls and columns, which are going to be solved using the 2008 ACI code. And by using LRFD and another strength design code, it means that I can use only strength level combinations in this model, and I don't have to generate the additional ASD combinations for this circumstance. Next, I'm going to flip over to the seismic tab of the global parameters, and all the variables that we input earlier for the seismic forces are already here. We also have a couple of additional variables as well, though. You can see that we have an omega overstrength factor and a rho redundancy factor. And we'll talk about those within the program here. So I'm going to hit OK, and let's take a look at just the lateral system in this building. The model's a little messy, so I'm going to come up and turn off the display of my nodes. Now, those of you who are familiar with the program may have actually noticed that we have some additional toolbar buttons shown up in here. Many of these toolbar buttons have been available since version 9 using the customized toolbar feature, but for version 9.1, we've actually set some new buttons as default up here, and you can actually set those defaults yourself in the existing version, or you'll automatically get them in the new version. And I'll be showing you some of the interesting features that come along with these new buttons. Now, when we take a look at this structure, what we find is that we have 4 moment frames running the length of the building. And I'm just going to render this for a moment so we can see a little more clearly. So we have these moment frames that are running in the global Z direction, and then we have some braced frames which are running in the global X direction. And all of this is sitting atop some concrete shear walls. All right. Now, one thing that we have to consider is the redundancy factor, the rho factor that we talked about earlier. And in general, in the code, what they prescribe is that the rho factor should be 1.0 for buildings which are not in the higher seismic design categories, the D, E, and F, and it should be 1.3 for those that are in the higher categories. But the intention of the redundancy factor is to account for buildings which don't have redundancy inherently in them. And so it's actually a penalty factor to use 1.3 since that's going to increase our seismic loads. But according to the AISC 7, if we have enough redundancy in our structure, we're allowed to use a 1.0 factor for rho. Now, how do we define that redundancy? Well, basically what the code says is that if I were to remove any brace running in the X direction, or if I were to remove the moment connection on any of these moment frame beams running in the Z direction, then I am not allowed to lose more than 33% of the strength of that floor in terms of seismic resistance. Now, clearly, because we have so many moment frames running in each direction and so many brace frames running in each direction, the failure of any one of those frames is not going to cause an overall failure of the structure. So therefore, we can be justified in using a rho of 1.0 for this structure. So that's what we're going to go ahead and do. Now, I'm going to go ahead and fire up the load combination spreadsheet, and we're going to create some load combinations for this structure. So for that, in the load combination spreadsheet, we'll pull up the load combination generator. You'll see that in the new version, we have the 2009 IBC compliance in here. So we have all sorts of new 2009 IBCs built in. And so I'm going to choose to generate roof live load combinations for gravity. You'll see I'm under the gravity tab. And then next, I'm going to come to the seismic tab. And in here, I'm going to generate only our non-overstrength combinations, since currently we're just looking at how the building works without the seismic provisions. So I'm going to generate 2009 strength combinations for seismic loads in the X and Z directions with the eccentric loads as well to account for building torsion. Now, I want these loads to be reversible since, of course, the earthquake can act in both directions. I want to include rho since that's mandatory, although rho will be equal to 1.0, so it's really the same as if I weren't including it. And I want to include the vertical effect of the seismic as well. So now when I hit generate, we'll see in the load combination spreadsheet here that we end up with these combinations. There's 28 relevant combinations for this. Now, I did not generate any wind loads because from experience working in Southern California here, the wind is definitely not going to control at all in a building like this. There's no need to clutter up my load combination spreadsheet with all the wind. All right, so I'll close out of the load combination spreadsheet, and I'll go ahead and I'll solve an envelope for this structure. And so we're going to run through an envelope solution right now with R equals 3 and without any seismic provisions applied, and we're going to see how well the structure performs. Now, actually, in this structure, I went ahead and I've set the member sizes in here. I've sized all of these for this exact situation. So when we solve this, we should find that all of the members work just fine, but of course they're not going to be meeting any of the special provisions. So as soon as this finishes solving here, right now we're actually taking care of the wall panel design, and I'll show you that in a second too. We actually are now designing the concrete shear walls. Once I finish with my solution, I'd like to review quickly that nothing in my model is failing. So the first thing I'm going to do is I'm going to take a peek at what my member sizes are. I can come up to this Member Labels button, and there's a little black drop-down arrow next to it, and I'm going to go ahead and choose Shape. And what we can see when I zoom in here is that we have some W16 by 36 moment frame beams up at the roof, W30 by 90s at the third floor here. We can see the braces are 10 by 10 tubes, and most of the columns in this structure are W14 by 145. Now, how do these actually work out? Well, we have this member color coding button, and if I click on the drop-down, I can color code all my members by their unity check, that is, their combined bending and axial. And we'll see, based off the legend in the upper right corner, that the worst-case members are magenta. That means they're 90 to 100% stressed, and when I zoom in, we can see a lot of these columns here are stressed at about 92 or 93%. But that means that they do all work. Okay, so now we've figured out that this building does work considering R equals 3, but of course we've determined that we're not allowed to use R equals 3 for it. So how do we design this building to meet all the seismic provisions? Well, the first thing we're going to take a look at is under the Materials Spreadsheet. You'll see that now under the Hot Rolled tab of the Materials Spreadsheet, we have some additional fields that weren't present in earlier versions. One of these is the FU, and this is the rupture stress or the tensile stress of the steel. This is now relevant to our design along with the yield stress that we previously had. And then we also have this RY and RT. And the RY and RT are ratios representing the expected yield stress, for example, over the stated yield stress. So in most cases, a steel that's listed as 36 KSI coming out of the mill is actually going to be about 50% stronger than that based on AISC testing. And when it comes to seismic, we're more concerned about what the steel's actually going to do, not with some conservative design values, so it's important that we apply these factors. The same thing goes here as well for the RT. This is the ratio of actual ultimate yield or ultimate stress over the reported ultimate stress. So we're going to go ahead and have to clear the results out of here now because we're going to apply some seismic design rules to this structure. Now, in order to do that, if you take a look under the data entry toolbar, you'll see that there's a new spreadsheet available called Seismic Design Rules. And if I click on that, these are rules that we can apply to different members within the structure in order to get them to be designed seismically. And there are 5 default settings within this spreadsheet. Now, I want to point out these are defaults. You can actually create any additional design rules yourself. These are just the 5 most common ones, so we ship these with the program. Now, if we take a look, here we have OCBF. That stands for Ordinary Concentric Brace Frame. And this is the Special Concentrically Braced Frame. We have an ordinary moment frame, an intermediate moment frame, and a special moment frame using reduced beam sections. So that's what these abbreviations are for. Now, under frame ductility, this is the ductility that these frames are to be designed for according to the provisions. And essentially, minimal always corresponds to ordinary, moderate always corresponds to intermediate, and high always corresponds to special. And you'll note we're on the column tab here, and so for the columns in these frames, this checkbox, overstrength required, is determining whether or not we should be designing the columns to those higher overstrength loads that we have there. That is, do the columns need to remain elastic during an earthquake? And the answer is yes, regardless of which one of these frame types we use, the columns always need to be designed for overstrength, so we have the box checked for all of them. Next, let's take a look under the Beam tab. Now, for our specially concentric brace frames, it's asking what type of moment connection we have at the ends of the beam. And the answer on that one is going to be none. And so we can choose none. And this is actually set to other none because if we do have a moment connection at the end of the beam, that moment connection will be checked for just the general moment connection provisions of the 341 code. Now, you'll note that beams don't need to be designed for overstrength in the brace frames. And these 2 values right here only apply to moment frames, so we don't have to fill anything in for those. Now, coming down here to the special moment frame, you'll see that we get to choose which type of moment connection we're using. And so in this case, we're going to be using a reduced beam section, but you can also use a bolted flange plate or an extended end plate, whether it's stiffened or unstiffened, or even a flange directly welded to the column. You can see here that in the case of the special moment frame, we do need to require overstrength on the beams, and we need to call out a Z factor and a hinge location. What do those mean? Let's go ahead and take a look. I'm going to go to a slide that I have here that's relating to this one on the reduced beam section. So this is an overhead view of a reduced beam section, and what we can see is that the beam flanges are coped at a point near the column. This is in order to force a plastic hinge to form near the column, but not at the column, because we're going to want this beam to actually form a plastic hinge to dissipate all of the energy in the structure due to the earthquake. Now, if we take a look here, there's a Z factor value, and that relates to the Z, the plastic modulus, at section A versus section B. You can see this is the point of most reduced beam section, and this is just the standard beam. And so this is going to basically account for how much of the flange we've coped out, and therefore how much rotational stiffness we're going to be losing in the beam. And then we take a look at the hinge location up here. This is the distance from the center of this coping away from the face of the column flange. So let's go back into the program now. And we can see that for this particular case, we're going to set our Z factor at 0.5. So I'm planning on detailing this connection later on so that we're going to lose exactly half of the plastic modulus due to the coping. And then I want that hinge location to be centered 18 inches away from the column flange. Now, this is fine if we're just going to be doing one type of beam, but if I have multiple beam sizes with multiple different details associated, I may need to create additional design rules that have different Z factors or different hinge locations depending on that. For example, I could call this one the special moment frame RBS W30, because for all my W30 beams, the hinge location will be 18 inches away, whereas I could create another line in here and call it the RBS W18, and I could give a different hinge location for the W18 beams. But in this case, I'm not going to be doing that. Just for simplicity's sake, we're going to use the same hinge location and the same Z factor for all the beams. Next, I'm going to come to the brace tab here. Under the brace tab, this really only applies to our bracing seismic design rules, and we can see whether or not we require overstrength for the brace itself and whether or not the brace needs to meet a special KL over R requirement. Now, what is this requirement? Well, this is one of the handy things in the program here. If I click within a cell in the spreadsheet, like this one right here, and take a look at the bottom, we list right here that this is the KL over R per 341, 13.2, or 14.2. So we actually give you a code reference directly here, and you can take a look inside the code to find out this is the limit on the overall slenderness of the brace itself. And so we do want to enforce that overall slenderness limit in this case, so I'm going to leave that box checked. So now that we've reviewed the seismic design rules, let's go ahead and apply them to our structure. So I'm going to color code my structure according to the seismic design rules, and I can do that by coming up to this member color coding button here, and I can choose seismic rules. And if I drag data entry out of the way, we can see the color coding. Gray is none, and then here's the different colors for each rule. So all my members are coded gray right now because by default, when I draw a member, it's going to come in with no seismic rules. Now I'm going to snap myself into an elevation view. What I'm going to do is unselect the entire model over here, and using my box selection tool, I'm going to grab only my concentrically braced frames and highlight those. Then I'm going to come up to Modify up at the top and choose Design Parameters. Now those of you who are familiar with this modification tool will also recognize that we can also get to it by going to Draw New Members and clicking on the Modify Design tab. This is where we can set various design aspects such as unbraced links. Now if we take a look down here, there's a new option here, Seismic Rules, and I'm going to choose Special Concentric Braced Frame and check the Use box. And I'm going to tell the program to apply this seismic rule to all my selected members. So when I hit Apply, and now we look, all the turquoise members here are specially concentric braced frames. Now the frames running in the other direction are still set as none, so we're going to need to set those as well. So I'll snap myself into this elevation view, and I'm going to select only the moment frames. Now you'll note that the columns in the corners of the building here, and these columns as well, are actually shared between the moment frames and the brace frames, but I know offhand that the moment frames have more stringent requirements than the brace frames, So it makes sense to set these columns as moment frame rules rather than as brace frame rules. So I'm going to do that. I'm going to come to Modify Design Parameters, and here we're going to choose the special moment frame as opposed to the special concentric brace frame. Apply to all members, and hit Apply. And so now these come in the reddish color, and so now we can see exactly how our seismic design rules are applied. Now down near the bottom of the structure, I still have these columns, and if I switch to a rendered view, you'll see those are concrete columns. Currently, we're not doing any special seismic detailing for concrete, so I just want to leave these as none so that they don't get designed for any of that. All right, so now that we've seen this, we will need to change the R values. And so I'm going to come back up to the global parameters, go to the seismic tab, and we can see that the R values have been set to 3 in this model, like I pointed out before. Now, the R values for a specially concentric brace frame and a special moment frame would be 8 and 6, respectively, but bear in mind that these are all sitting on top of concrete shear walls, which are going to have an R of 5. And according to the code, if we have different R values throughout the height of the structure, we actually need to use the most stringent, or in other words, the lowest R value, respectively. So because 5 is less than both 8 and 6, we're actually going to need to set the R values to be 5 in this structure. Now, the overstrength factors, we also need to use the most stringent ones, and so that means that in the X direction, we're going to be using a 2.5 times overstrength factor, and in the Z direction, we're going to be using a 3 times overstrength factor. So now I'll hit OK. We've adjusted our R's now, and the program just lets me know that changing the R values is going to cause the seismic load to be updated, and that's good. That's exactly what we want. So next, I know for a fact after solving this model earlier that my existing member sizes are not going to work with the new seismic provisions installed on here. So we're going to have to make a few changes to those. I'm going to come back up here and turn on my member display by shape again. And what I've done in this model is I've used the Save Selection States in order to put together a few selection states. And you can come over and use this green button to create or retrieve any of these such states. So, for example, when I take a look at my light beams, which I retrieve, these are all of my moment frame beams up at the roof, and then they're also my brace beams here, and we can see that I'm using a W16 by 36. And that size I've actually found is going to work for both circumstances, so we can leave that as is. I'm going to retrieve a selection state of heavy beams. These are the moment frame beams down here. Now, previously, when we didn't do any seismic detailing, these worked fine as W30 by 90s, but with the seismic detailing, we need to have some additional stoutness to these beams, and so we're going to actually bump these up to be W30 by 108. So I'm going to come to Modify Members, and this is the Modify Properties of the Draw Beams tab. And basically, I can check the Use box to change only the member size, and we're going to set this to be a W30 by 108. And I'm going to apply this to all my selected members, which are just those beams there. All right, next is the columns. When I take a look at what I'm calling my light columns, these are just the columns that are only part of the brace frames. A W14 by 74 will still work just fine. And if I take a look at my heavy columns, these are the columns that are part of the moment frame. Currently, with no seismic detailing, these work great as W14 by 145. But we'll find that the columns really need to be bumped up quite a bit because they're being designed for those overstrength factors. So I'm going to actually have to come up to here and modify members and change these column sizes from a W14 by 145. We have to go all the way up to a W14 by 233 to get these just to pass. So now I'm going to apply that. And so at this point, now I can generate some overstrength load combinations. So I'm going to come up to my data entry toolbar, load combination spreadsheet. And now we already have the ordinary row seismic combinations created. I'm going to go back to my load combination generator. I'm going to hit none since we don't need to regenerate the regular seismic loads, but I am going to choose X and Z with eccentric, reversible, and with vertical effect on my overstrength combinations, so that when I hit generate, we now get additional load combinations shown down here, which have this overstrength factor. Now, these load combinations will only apply to members that have overstrength assigned to them. All the other members will be designed using the non-overstrength load combinations. And you'll see that we end up with a total of 52 load combinations. So next, I'm going to go ahead and solve an envelope in this. So what we're going to do is run through all these different load combinations here, and you can see the program's doing that right now. And it's picking out which members are part of seismic design rules and which ones aren't. The members that are not assigned as any part of a seismic design rule will ignore the overstrength combinations, and they'll be designed the same way that they've always been designed within the program. So you don't need to worry about changes happening to existing models, for example. You're still going to get the same performance on ordinary structures. We've only added these additional capabilities for the seismic structures. Now, on the seismic structures, the columns will get designed for these overstrength combinations here. But since I didn't specify overstrength for any of the braces, we won't get any of the braces designed for that. So it is sorting through all of that as it goes through and figures out all the code check information. And while it's at it, it's also figuring out a variety of different aspects related to the specific detailing of how these members come together. So we're running through the solution right now, and it's finishing up the concrete wall panel design and the concrete column design. Now let's check real quick to make sure, first off, that our concrete walls turned out okay. If I come under here to my results wall panel design, we can see that both for in-plane and out-of-plane, our unity check on the concrete walls is less than 1. So that means that we don't need to worry about that. Those have now been designed correctly with the correct rebar. But coming back to the steel, we want to make sure that that's coming out correctly. So I'm going to come back up to my member color coding and once again take a look at unity bending. And what we find is with these increased column sizes that we're now at about 95 to 98% stressed on the columns, and all of our beams, none of them are in the red up here, so none of them are failing. So we're working out okay in terms of strength, but we're actually going to want to review a variety of detailed results. However, unfortunately, when we take a look in load combinations, you'll find that we have 52 different load combinations. And when I solve an envelope, I can't look at detailed results for each member. I'm just getting worst case for all the members. But in my experience, I found that even though there are 52 mandated load combinations within the code, not many of these are actually going to be controlling my design. And there's an easy way to actually filter out the load combinations that are not going to be controlling. This is a little trick I've picked up on the side here. What we do is come to the results toolbar, and I'm going to go to my design results spreadsheet. And what that's going to do is for every member that I have in my model, I'm going to get a code check on that member, and I've solved an envelope, so I'm also going to get what load combination caused that code check. I'm going to go ahead and highlight this entire load combination column and copy it. Then I'll open up Microsoft Excel, and I'm going to paste that in here. So now this column right here in Excel contains every load combination that controlled a bending check within my model. And what we can do is we can sort that data, and then Excel has this handy function I like here called remove duplicates. And when I do that, it's going to get rid of the redundant values within my model here. And what we end up with is we have this short list of load combinations here, 10 of them, that actually controlled anything. You can see it's LCs 2, 4, 6, 7, 12, 13, 33, 34, 39, 40. So now I'll go back into RISA-3D, and if I go to my load combination spreadsheet, you'll see we have solve set for all of these. I'm going to highlight the entire solve column in the spreadsheet, right-click and say Fill Block. And Fill Block allows me to fill all of the cells in a given spreadsheet with any data that I punch in. And if I leave this blank, then it's going to fill all these cells with blank, and blank is the same as unchecked. So now we've unchecked all of the solve boxes, and solve determines whether or not this load combination should be solved as part of a batch or an envelope. Now I'll come back to the numbers that we received from Excel previously, and we know that load combination 2, 4, 6, and 7, 12 and 13, 33, 34, 39, and 40 were what controlled in this model. So out of the 52 load combinations, 10 actually controlled, and the rest were just extraneous. We'll leave them in the spreadsheet here, but we really only need to solve these 10. So now I can actually go back, and I can solve a batch solution. And it's only going to solve those load combinations, which is going to make this much quicker. And that's part of the point to it as well. Certainly when you get into very large models and you've got hundreds of load combinations prescribed by the code, you're going to want to be able to get through these solutions quickly. And you can see how much faster that went when we only solved the 10 load combinations as opposed to 50. So now that we come back out here, we're seeing the batch solution results, so we can actually take a look at member code checks per load combination. And obviously the first load combination displayed, which is just dead plus live load, isn't going to show a whole lot of stress for most of my members listed on here. So the next thing we're going to want to do is take a look at the results. And I'm going to go back to my PowerPoint for a second here so that we can talk about what results we're going to be reporting within the program. Now, the AISC requires us to check member strength and slenderness, connection strength, some miscellaneous checks such as strong column and weak beam ratios and span of depth ratios, and then there's also a number of fabrication detailing requirements within AISC as well. Now, we will report to you checks on everything listed here except, of course, for the fabrication detailing requirements. These are things like limitations on welds that can be applied. There's a variety of different special things, protected zones at the ends of beams. We really don't get into that much detail with regards to that. That's something that we would expect the fabricator instead will deal with. And, of course, the RISA products are set up to be used by the engineer more so than by the fabricator. So let's go back into the program and take a look at our results. Now, we want to take a look, aside from the overall member results, and that was our unity checks for our columns and beams and the such, we're also going to want to take a look at how things did in terms of seismic. And so I'm going to come down to the seismic detailing spreadsheet of the results tab. So I click on that, and we pull up this spreadsheet which summarizes all of our seismic detailing results. So the first thing we get is in the columns tab, here's the label of all the columns that had seismic design rules applied to them. We see the seismic design rule that was applied, the ductility required. Now this is all just data that's being echoed back from our input. So yes, all these columns here are part of special moment frames, and they all have high ductility because it's a special moment frame as opposed to an intermediate or ordinary. We see the UC max for the column and the load combination, and that's the same as what was reported in the design results spreadsheet. We get slenderness checks. Now, the slenderness checks in a column are going to relate to whether or not the flanges or the webs are considered to be slender or non-compact as opposed to compact or seismically compact. This all relates back to how the columns are intended to fail during a seismic event, and according to the code, the columns are not allowed to have slender elements within them, and so we check to make sure that none of them do. And as we can see, it looks like everything is passing in here with regards to that. Now after that, we do actually see some fails listed here, and this is under the panel zone checks. We can see that some of my panel zone checks are failing, and we get the fail listed and then the beam that caused the failure. So this means that the actual web of the column in the panel zone is failing due to shear. And we report right here what equation from the code was used. And you'll see that actually it's using an equation from the regular AISC 360 as opposed to out of the 341 to check for that. Now what this also means is that you can actually use this seismic detailing feature to check panel zones on columns even if they're not seismically part of a frame like this. You can actually now do panel zone continuity plate checks for moment connections on even wind-controlled columns within the program, and it'll use these equations for you. But today we're looking at seismic, so let's look at that. We can also see that continuity plates are required. So it says, yes, continuity plate is required. And so these plates are going to go between the flanges in order to connect across a moment connection and keep you from getting things like local flange or web crippling of the column. And we can see those requirements listed there as well. Now, having these requirements here means that we're going to have to add web stiffeners and we're going to have to add continuity plates into the columns, and that usually ends up becoming very expensive in terms of fabrication. And so we might want to take a look at how to turn these into clean columns, which is columns that don't need any special fabrication detailing. So what I'm going to do here is we're going to come up here to my member color coding, and one of the options that we have now is the column stiffener check. And when I choose that, we get all the columns color-coded on whether or not they're green, which is clean columns. They need no special detailing, and we can see those listed there. The blue ones are going to require continuity plates. The pink ones require web doublers. We have none of those. But we do have a number of red columns, which means that both web doublers and continuity plates are going to need to be installed on those columns. That actually ends up becoming very expensive. Let's find out if we bump that column size up, if we can actually get rid of that requirement. What I'm going to do here is I'm going to retrieve my saved selection state of all my heavy columns here, most of which are red. I'm going to come up here to modify members, and we're going to change this column size from a 14 by 233 to a 14 by 257. And so when I set that and apply to all these selected members, now I can solve my model again for the batch, and we'll see whether or not that changed things. Now, granted, we have gone up 24 pounds a foot in a column just in order to get rid of possibly some certain detailing. But I'm sure that if you compare the costs, increasing the column weight by a little bit in terms of the price of raw steel is nowhere near what it'll cost to have all sorts of extra web doublers or continuity plates welded onto those columns and specially fabricated. And sure enough, we find out here that these columns have now gone from red to pink, which means that they do require web doublers, but they will not require the continuity plates anymore. And actually, all of our exterior columns now are listed as clean columns, or at least the ones that are part of the brace frames. Now, in my experience with playing around with this model, what I have found is that you can bump these columns up to extraordinarily large sizes and still need web doublers in them, so there's probably going to be no way of getting around that, but at least now the program's able to notify you of this fact. Now, let's go back and take a look at some more seismic detailing results. The other things that we'll find out are the strong column weak beam ratio. And the intention behind this is that we're going to want plastic hinges to form in the beams as opposed to the columns during an earthquake event. And so we want the columns to be stronger than the beams. And so this ratio shows us the strength of the columns to the strength of the beams. And as long as that value is above 1, it means that the columns are stronger than the beams. And so we're going to get the sort of behavior that we want. And we can see that it passes for everything since the values are all above 1. And then lastly, we have the miscellaneous checks reported. These are all reported as pass as well in this case. Now, the next thing we're going to get out of our seismic detailing summary sheet is information on the beams. When I come in here, we'll see there's your beam label. Once again, seismic design rule and ductility reported back to us. The unity check and the load combination that controlled reported back to us. Slenderness checks. Looks like all of our beams passed just fine for slenderness. Now here's our moment connection type. We have reduced beam section for many of these. These other beams list other none. That's because those are the brace beams that we have in our structure. We also have a required shear and a required moment. And these are going to be the connection design forces. I mentioned earlier that we're going to give you connection design forces even though we don't fully design the connection in the program yet. So for now, you'll get that this beam is going to require about 15 kips of shear and about 202 foot kips of moment for its design. Here we get the strong column weak beam ratio reported once again. We have a span to depth ratio reported on here. And that is because the AISC 358 gives us pre-qualified moment connections. And these are connections that have been extensively lab tested. And so the reduced beam section connection has actually been tested quite a bit, but only within certain span to depth limitations. Outside of that, the AISC is not entirely certain about its performance. So for that reason, we have to check to make sure that your span of depth ratio for your frame actually meets the ratios that have already been tested and confirmed that work correctly, and that's listed as pass. And then lastly, we have the miscellaneous checks, and we have those listed as pass as well. Next, I'm going to go to the braces tab up here. In the braces tab, we're going to report the brace label. We're going to give you, once again, the seismic design rule assigned to it, the frame. We get the unity check and the load combination, slenderness checks on the braces, and then we get this information right here. This is the required tension and required compression on the brace. Now these are the design forces for the gusset plates at the ends of the brace. And so we can see that we have some very high forces that those gusset plates are going to need to be designed for. The reason behind that is that the code has basically stipulated that failure in a brace during a seismic event should occur in the brace itself, not within the brace's connection. Therefore, the actual connection of the brace needs to be designed for higher forces than the brace itself could ever take, and that ensures that you wouldn't get, say, a gusset plate buckling, which is a rather non-ductile failure mode, as opposed to an overall brace buckling, which is a non-ductile, or which is a ductile failure mode. Now, aside from that, we also have this value reported called unbalanced vertical force and unbalanced beam. What is this relating to? Well, this relates to all of my frames which have multiple beams or multiple braces intersecting a beam, such as this inverted V bracing that we see right here. So with this inverted V bracing, let's take a look at a slide that illustrates what we're dealing with. Picture that we have this brace frame right here with these two braces that connect to this beam. And the braces have a tensile capacity of 200 kips and a compressive capacity of 100 kips. Now, when I push on this frame, until I get to the point where a brace buckles, we have a free body diagram on the beam which looks like this. We have a force coming up and a force coming down, resulting in no net vertical force on this beam. So all the vertical force in this brace is taken in this brace. Now there is a net horizontal force, but that's what we're used to designing for, the axial force in the beam. What the seismic provisions tell us is we need to consider this case down here where we've pushed on the frame so far that this brace is actually buckled. And this is actually the sort of behavior that we're going to expect during an earthquake. And what we're going to get is that at maximum utilization of this frame, in other words, when it's pushed over as far as it can, you're going to have a tension in this brace equal to its tensile capacity, which is 200 kips. And you're going to have this brace already buckled. And when this brace is buckled, it's still going to carry a little bit of force, but a lot less than it ordinarily could because it's already gone beyond the buckling point. And so they say that value is 30% of the brace's buckling capacity. So therefore, when we look at a free body diagram for this situation, here we have the same tensile force as ever on this end of the beam, but then on this side, the resisting, we have a much smaller force, and so the difference needs to be made up in terms of internal beam forces. So what we end up with is that some of the tensile force in this beam is resisted vertically with this brace, but that some of the tensile force from this brace is actually also resisted as shear in the ends of the beam, as this whole beam is now going to get pulled down or pushed up accordingly during the earthquake. So we need to design the beam for this unbalanced force. Now at this time, in the program, we do not actually design the beam for this unbalanced vertical force. However, we do report it to you so that you can take care of that design separately on your own. Then lastly, we have some miscellaneous checks that are associated with the braces here. And next, we're going to take a look at values that are going into a bit more detail. So I'm going to come back to my columns tab, and let's take a look at this column right here, which is at A2, and let's just zoom out a little bit. This is going to be this column right here, and let's pull up a detail report for it. I can do that either by being in this spreadsheet and clicking Detail Report for Current Item, or by going out to the Model View and clicking on the white Detail button to view that detail report. And what we get is the same type of detail report that we're used to seeing on these, and here we can see this column is about 88% stressed. And scrolling down, these are the same values as we've always gotten. Here's the LRFD code check based on axial, tensile, bending, so on and so forth. And this is including overstrength forces, and we can actually confirm that by taking a look up at the top where we report the controlling load combination 33, and we have this omega in parentheses. That's an overstrength combination. Now coming down a little farther, here's some information on the seismic detailing results. So these are the results for the 360. Here's all of our results for the 341 and 358 codes. So we can see this member type as a column, same information echoed right back to us. It is intended to be designed to the overstrength loads. Now we can see that the flanges and webs are considered to be seismically compact. This is actually a B over T ratio that comes out of the code. And it's considered seismic compactness because it's more stringent than the ordinary compact limit that exists in the 360 code. Coming down a little farther, we have an L over R limit. This is a slenderness limit on the overall column that needs to be less than 60, and we have met that. Now coming down a little farther here, we're going to get a panel zone summary, and so here's where we get that panel zone design that said earlier that we needed web doubler plates. As we can see, here's each beam that comes into this column. We get a shear demand on the actual panel zone or the web itself due to that moment connection, and then we get a capacity reported as well. And so we can see that for the beams on floor 2, we are going to need that web doubler plate because the unity check, that is the shear demand on the panel zone over the capacity of the panel zone, is about 60% overstressed. But actually at the roof, we're not going to need to add those web doubler plates. So that's a good sign anyhow. Scrolling down a little farther, here's our continuity plate summary, and we can confirm that we don't need any continuity plates or flange stiffeners in this model. And we get all of our calculations reported as well as exact code references for each one if we need to come back to them. Now you can see where this detail report may get a little bit cumbersome, which is why we've given you this sort of summarized seismic results spreadsheet that's shown in the background there. Scrolling down a little farther, here we get the column to beam moment ratio, and this is the strong column weak beam ratio, and we can see everything passes. And then we also get information here on the column flange bracing force, and so this is going to be the force that's going to, the bracing is going to need to be required wherever we have these moment connections in order to keep the column from sort of kicking out sideways. So we get that information as well. Now let's come down to another column here, and I'll take a look at one of the brace columns. So this is the SCBF, and we'll look at the detail report for this one. You'll see it's a lot more succinct because we don't have any moment connections on this column. All the panel zone checks and the flange bending checks and web crippling and all that are all omitted because this just has shear connections coming into it. So it's a much simpler output for that column. Next, we'll take a look at some of the output for the beams. So I'm going to flip over to the beams tab here. And what we have are our moment frame beams to begin with. So let me go ahead and pull one of these up. I'm going to get a detail report for it. And so when I scroll down, we see this is one of my W16 roof beams. And we can see here that on this beam, we're fine in terms of the regular checks. Now, in terms of beam checks that we get reported within the program here, we can see that the compression flange is non-slender. These are seismically compact. And I'm not seeing anything reported at me in red, and so that means that nothing's going to be failing on this beam at all. And we would have seen failure as well reported here as fail instead of pass. Coming down a little farther, we get our beam flange bracing reported here. Now, this is the bracing that's going to have to occur on the beam due to this bending. What we get is the required strength of the bracing. Now, in this program, we've just set the LB values, but we never really specify what exactly is bracing it. It's up to you as the engineer to use this information to figure out something that can actually brace the flange. So we can see, according to the AISC 360, this flange bracing needs to be at no more than 75 inches on center, that the strength, the axial strength of whatever's framing into that flange, needs to be handled about 2 kips per the AISC 360, but per the AISC 341, right adjacent to the plastic hinge, that is where our reduced beam section is occurring, we're going to need to have a brace that can handle up to almost 7 kips of axial force. And so we may actually need to come in with a single angle kicker or something along those lines to get that braced. We give you this information so that you can handle the specific detailing on your own. Now, we also get a required stiffness as well. If that brace that we put on there axially, maybe it's a single angle, can't handle more than 20 kips per inch of deflection, which seems like a pretty easy requirement to hit, then it's not going to work. But nonetheless, it is important to consider that. When I scroll down a little farther, we get our required connection shear strength reported. So what we see here is, first off, this omega VU, this is the maximum shear that occurred due to overstrength combinations in our model. But we get another value here, and this is the VG and the VPR. This is the probable shear, and this is essentially the maximum shear that's going to exist at the face of the column due to that plastic hinge forming, and the VG is the maximum shear caused by gravity. And according to the code, what we do is add these values together to get a shear design strength of about 15.6 kips that needs to occur at the end of that beam. So now we can design our connections for the appropriate seismic load that's going to be on there. Then coming down a little farther, required connection moment strength. Here we can see the hinge location and the effective plastic modulus. And from that we can figure out actually what the plastic hinge moment is going to be at the face of the column. And then using that and the shear caused by that plastic hinge moment, we can see that we're going to need to design this connection for 202 foot kips, even though the maximum moment that actually occurs in the model is only 120 foot kips. This relates to the fact that, of course, our connections in seismic need to be designed much stronger than the actual beam itself. That way we can ensure that the beam fails and not the connection, and thereby get that ductile failure as opposed to a brittle one. Next, we'll take a look at one of the brace beams. So I'll click on that. We'll pull up a detail report for it. Scrolling down a little farther, similar results to what we saw before. Now in this brace beam right here, we get a couple pieces of information. Here's just the standard information. And we can see here on this brace beam that the unbalanced force on the beam that we report is not considered in the beam code check. So that's important to remember that. And here you can see we actually point out which braces frame into this beam, M97 and M98. There's their respective compressive and tensile forces. And here is the resultant horizontal and vertical component on this beam. And we also get a warning on this beam that the seismic connection, no weak axis moment connections are allowed, But we can actually ignore this warning here because we don't have a moment connection on this beam going into the weak axis of a column. This is actually set up as a pin-pin beam, which we can see based on the shape of the moment diagram there. Next, I'll flip over to the braces tab. And under the braces tab, we're going to pull up a detail report for one of these braces here. I'll go ahead and pick this one. And when I scroll down within here, here we can see all this similar information reported. So we can see that this brace is set up as compact, that we do meet the KL over R requirements. Here's our required connection axial strength, and so you can see this is the gusset plate design we talked about earlier. For compression, the gusset plate and the connection of the brace end needs to be designed for 1.1 times RY times PN. So PN is the compressive capacity of the brace itself, so we need to be 10% higher than the compressive capacity of the brace itself, plus with that extra RY in there to adjust for the fact that the actual strength of the brace is going to be higher than what we designed it for because the steel material itself will be a little bit stronger. Here's the tensile. Same idea applies here. And so we can see that the actual maximum brace force that we ever get here is about 146 kips, as opposed to the 700 or 800 we need to design the gusset plate for. And this plays in the gusset plates a lot, but currently we're not handling those in the program. We are at least giving you the forces that are associated with it. And then here's the unbalanced beam forces reported once again for this brace configuration. So we can see everything else is passed in this model. And so actually, overall, we are looking quite good in this model with the exception of these panel zones. So we've now confirmed that we can actually have this model considered to be special moment frames and specially concentric brace frames, and we're going to meet all the requirements of the AISC 341 and 358, and we have adequate output here that you can actually print these out and submit it to a code official to prove that you've run through all of these checks, which would be otherwise very tedious and difficult to check by hand. Now, one other thing I want to point out, and this is just from the seismic detailing spreadsheet, I can hit F1, or you can always go to Help up at the top of the program and find that we have a new seismic detailing topic. We've written up an extensive help file on this when we created the feature so that you can go in and actually get a lot of different information as to where these checks come from. We explain a lot more in depth in this help file about exactly what each check is and what the intention from the code is and how we've interpreted everything. And so this is some very valuable information to know in case you want to know any details about what we're doing within the program. So I'd always definitely recommend checking out the help file. And remember that anywhere within RISA-3D, you can always just hit F1 to pull up help. Now, the only other important thing to point out here is that when I go to the members spreadsheet, you'll see that because I'm working underneath RISA floor, the type for each member is actually set automatically by RISA floor. So you'll see, for example, this beam right here is set to beam. Now, by default, when you draw members within RISA-3D, they always get drawn as beams unless you specify otherwise. So when I come up to Draw New Members here, under the Draw Members tab, we actually have to tell it whether it's a beam, column, V brace, or H brace. And I see a lot of people just leave this alone and call everything a beam. Well, that's fine in terms of code checks for regular structures because the AISC doesn't differentiate between what is a beam or a column in terms of capacity. However, for seismic checks, it's very important that we see what is a beam versus what is a column. And one way I can actually check in the program is by coming up to my member labels option here, and I can take a look. Actually, that option is not available up through there. It looks like it's available through the plot options. Okay, so it's under the color-coded. If we go to the plot options in the upper left corner, the blue button, color basis, I can color code by member type. And so now I can see the green ones are beams, the red ones are columns, and the pink ones are going to be vertical braces or V braces. That's as opposed to horizontal braces, which are braces existing in the horizontal plane. That would be for like diaphragms and the such. So it is very important when you're modeling now, of course, to assign the correct member type, and then don't forget to assign your seismic design rules as well. And that basically covers everything you need to do in order to meet all the requirements of the new code there. Now, we do have some additional resources, as I've just pointed out. Aside from the help file and the printed general reference manual, we do have a website, RISAnews.com, and RISAnews.com has a lot of quick tips for things in the program. We have a wide variety of short articles posted up there. And then, of course, there is always the AISC Seismic Design Manual, which you can read through if you have any further questions. We'll give you all the code references directly within the program. And as I mentioned, this new version is just coming out, actually either later today or tomorrow. We'll wait and see how quickly it uploads to our website. And so those of you who are under maintenance, go ahead and go pick that up. And if you are unsure whether or not you're under maintenance or whether you're going to be receiving it, you can always give us a call or shoot us an email over here.